The Math of Foucault Pendulums. So this is the first video of a 3-video series on Foucault pendulums. The first one is just going to be focused on the math of pendulums in general, but then specifically Foucault pendulums. The next one is going to be DIY, how to make your own Foucault pendulum. And then the third video, I hope to show my results. I have not actually made the Foucault pendulum yet, so I'm crossing my fingers that I hope it'll work. Math of the Foucault pendulum. We're going to divide this into 2 parts. The first part is going to be just on math of pendulums in general. The second part is going to be focused in on the Foucault pendulum. So part A, how does the pendulum work? We're first going to talk about potential energy, the different forms of potential energy, and the conservation of energy in a pendulum, which is basically how the pendulum works. And then we're going to figure out the pendulum swing, the period of the pendulum swing, and then do a little analysis with drag and friction, which are going to slow our pendulum down. In part B of this video, we're going to focus in on the Foucault pendulum. So we're going to have a refresher on the Coriolis effect, and then we're going to look at the period of precession of a pendulum using the Coriolis effect. We're going to start with an example pendulum in Cairo, sort of a thought experiment, a 14-mile tall Cairo pendulum. And we're going to use that to derive the actual formula for the period of precession. Then we're going to use angular velocity to try to derive the formula for period of precession as well. So let's start off with part A. How does a pendulum work? Well, it all starts with forms of potential energy. So specifically starts off with gravitational potential energy. But oftentimes they'll just say potential energy, not realizing that there's more than one form. So there are several forms. We're only going to cover a couple here, such as chemical potential energy, like fuel, or mechanical or elastic potential energy, like a cocked spring. And can you tell what's wrong with that die? Or we can have electrical potential energy, like the energy stored in a capacitor, like in a stun gun. And then the most important in our consideration is the gravitational potential energy. So imagine a roller coaster at the top of a hill. It's got a whole lot of potential energy to go really fast. So the potential energy formula is mgh, mass times acceleration due to gravity times height. All right, so now we're going to talk about how a pendulum actually works using conservation of energy. So here's a different roller coaster. So when you're nearing the bottom of the hill, you're probably going really, really fast. So your potential energy got converted into kinetic energy. So kinetic energy is 1/2 mv squared. Now, here's a simple diagram that shows the exchange between potential energy and kinetic energy. So on the far right-hand side, we're at all potential energy, and at the very bottom, we're at all kinetic energy. All right, so when the bob is at the right, we have the mgh formula, and then when it's at the bottom, it's 1/2 mv squared. So it's constantly transferring energy between potential energy and velocity, or kinetic energy. So at any given point in time on the pendulum's path, not just the ends, but anywhere along the pendulum's path, the total energy of the pendulum is equal to the kinetic energy plus the potential energy. All right, so you've got conservation of energy going on here. And this is actually the full diagram. Notice on the far right, it says that the kinetic energy is 0, but that the potential energy is mgh. Now at the very bottom, letter B, it says that it's all kinetic energy. The potential energy is 0. But there is an error in this diagram. Can you find out what it is? Here's an idea for a future video. So if you are given the height of a pendulum bob at the end, predict the speed of the bob at the bottom of the swing. And sometimes people are talking about density and buoyancy, so it'll be interesting to try to figure that out using density and buoyancy versus kinetic energy and potential energy. Next, we're going to talk about the period of a pendulum swing. Now, this is going to be distinct from the period of a Foucault pendulum. So the period of a pendulum swing is just the out and back. You pull a pendulum back, you let it go, and it swings out and back. That's the period that it takes for one complete swing, out and back swing. All right? And the formula is kind of interesting looking, but it's fairly simple, and it's a really an incredible formula to derive. So this fellow, Sam Hite, does a really nice job. It's an 11-minute long video, but definitely check that out. But the important thing, and for our purposes, is that the only thing that you can manipulate in this formula is L, or the length of the support string or the wire. So if you want to have your pendulum go slower, have a slower period, you simply make the wire longer. And then lastly, we're going to talk about what is going to slow our pendulum down. Because again, the goal of this video series is to talk about Foucault pendulums and to have you guys make your own Foucault pendulum. So we're really interested in what causes a pendulum to slow down and stop. We will not be able to get a very good result if we start our pendulum swinging and then 5 minutes later it comes to a rest. All right, we really want our pendulum to be swinging for a long time. So we need to take a look at drag and friction equations. Here's the drag formula, the force F sub d, force of drag. And it's got a bunch of values in it. One of them is the coefficient of drag, which you have to find using a wind tunnel. But for our purposes, we're going to take a look at the velocity and the area. So as the velocity increases, the force of drag is proportional to the square of the velocity. Now that's incredible. So if your pendulum is going twice as fast, that means the drag is going to be 4 times bigger. That's why you'll see if somebody takes a pendulum and they swing it like really far, like they pull it really far back, it comes down, the speed gets knocked down very, very quickly. It loses a lot of energy because of drag. So that's something to keep in mind. The other thing we want to keep in mind is cross-sectional area. So drag force is definitely proportional to the cross-sectional area. The bigger your bob, the pendulum bob, the more the drag. All right, so we'll definitely want to minimize that. Next, we're going to talk about how this drag force actually slows our pendulum down and what we can do about it. So as the pendulum is moving, there's always going to be a drag force in the opposite direction of the motion of the pendulum. This will happen if the pendulum is not in a vacuum chamber. So since we can't affect the force of drag, and we want to minimize deceleration, right? The letter A, F equals ma. The thing that we can affect is the mass. So if we make the mass as large as possible, then for a given drag force, we will be minimizing the deceleration. Now let's talk about how else our pendulum can slow down with either bending torque or frictional torque. So the Newton's cradle on the left is essentially made of fishing lines. So literally those little fishing lines are bending at the top support. Now you may not think this is much, but there is a little bit of bending torque that is going to slow this thing down. On the right hand side, you see a tire swing or tire swing set, which has a little swivel at the top, and that, maybe it's well greased, but that does have a little bit of friction to it. Now those are very tiny elements. How much of the fishing line is being bent, a very tiny amount is being bent, and that swivel is a very tiny amount compared to the actual tire swing set. But what does that translate to? It translates to torque where the pendulum bob is. So the pendulum bob is at the end of a length of either wire or string. Well, that's where the torque is going to have an effect. All right. So the motion of the pendulum again is in purple. Now the resistance due to torque is in orange. Now, how do you find that torque? It's essentially the force times the length, right? The force times the length. So if we have some source of torque at the very, very top, we can minimize that by making the length of the pendulum as long as possible, all right? Because if it's force times length, if you increase length, you have to decrease the force. So the resistant force, that orange arrow, will be minimized if the length is maximized. Alrighty, so let's kind of give an overview of the math of a pendulum, and specifically the math of a long swinging, long running pendulum. So again, the initial energy you give to a pendulum is based on potential energy. That's when you pull it back, and then that gets converted to kinetic energy, and this is constantly in equilibrium. But if you have a faster swing, you have a higher drag. So we really want the bob to be moving slowly. Now the period of the swing is proportional to the length of the wire. Well, if we give it a longer string or a longer wire, that's going to swing slowly, which means it's going to be moving with a slow velocity, giving a slower drag. Also, the larger the bob size is, the bigger the drag with the air. So we want as small a bob as possible. And the drag has less an effect with a bob of higher mass because of momentum. There's also torque, either frictional bending torque or frictional torque, and this is also going to be minimized with the greater distance to the bob, like the length of the bob's support. So the best combination is a long support wire and a heavy and small bob. So something dense like steel or lead. You want to do that. You don't want to do like a rubber ball or a styrofoam, ball or something like that. All right, long support wire, heavy and small bob. And we're going to go into much more detail in our second video, the DIY Foucault pendulum. Part B, the actual Foucault pendulums. Now, again, this video is focused on the mathematics of it. So let's take a look at how we're going to analyze the math. We're first going to start off with a refresher on the Coriolis effect. So there are some people who just want the globe to die, but if you take the globe, you realize that if the globe is turning once on its axis per day, approximately, that the higher latitudes are going to be turning with a slower velocity. So that red hoop is literally a smaller circumference than the green hoop. All right? So if the Earth is turning once per day, somebody on that red line is going to literally be moving slower than somebody on that green line. And that's where the Coriolis effect comes from. So if we have a cannon on the green line and we're aiming it at the red line, and we fire that cannon, well, it's going to miss. Now, you might have missed it, so I'm going to slow it down, and I want you to focus on that red dot, and I want you to see if that red dot looks like it is curving away from the target. So watch the red dot, and see if it doesn't look like it's curving away from that target. But in actuality, it wasn't curving at all. That red dot was moving in a perfectly straight line. But because the target was moving slower, it appeared to deflect the projectile to the right. So in the northern hemisphere, projectiles deflect to the right. All right. Well, what if you flip the globe upside down and have the south pole at the top? The Earth's rotation is going in the other direction. Well, projectiles will deflect to the left, as we see in this case. So if you're shooting a cannon over Australia, you might have an accident. So you just got to be careful that you're taking consideration of the Coriolis effect. All right, so now we're going to deal with our thought experiment. We're going to build a 14-mile tall pyramid in Cairo, Egypt. And we're selecting Cairo because it is exactly at 30 degrees north latitude. So we're going to build a structure kind of like the St. Louis Gateway Arch, 14 miles tall. So there it is, and we're looking in a northern direction. It's going to have a north-south swing, so it's 14 miles tall with a north-south swing, and it's on 30 degrees north latitude. All right. So because it is so tall, it's going to have a very significant swing length. So the swing arc is going to be 2 miles, or a 1 mile radius of the swing arc. All right. So there's our pendulum, 30 degrees north, and there's what the swing arc might look like. But we're focused in on the Coriolis effect. So let's take a look. The mount of the pendulum, the arch, the purple arch, is going to be moving at one velocity, but the Earth underneath the end of the swing is going to be moving at a slightly slower velocity. That's where the Coriolis effect is going to come from. So if we draw the axis of the Earth, and we draw the radius of the purple, and the radius of the green, we can actually figure out these circumferences and actually perform some math. Now we're taking a look at a top-down view. Notice that the bob, the green bob, has slightly deflected to the right. All right, it's deflected slightly to the right. And we can actually measure that Coriolis effect in miles per hour. Now, once we know the miles per hour, we can use what's called the radius of the swing envelope. Now, the swing envelope, so if you have a pendulum and it can swing freely in all directions, in other words, it's not like a grandfather clock that it can only swing left to right. If your pendulum can swing in all directions, then you might have a swing envelope. And again, that's the whole point of a Foucault pendulum, is the Foucault pendulum, the swing, the back and forth swing is actually going to go in a circle. So if we have the size of this red dotted circle, we can actually find the period of precession. So let's actually run some numbers. So here we are in Cairo, Egypt, which is 30 degrees north latitude. There's our pendulum swinging, and let's run the numbers. So we've got a nice right triangle, a 30, 60, 90 right triangle. If the hypotenuse is the radius of the Earth, then that long leg is going to be root 3 over 2 times the radius. All right. Now the swing, the radius of the swing is 1 mile. All right. 1 mile north is where the end of that bob is going to end up. Well, that's at a higher latitude, which is a shorter distance from the radius of the Earth. So let's figure out what that distance is. We construct a similar right triangle, another 30, 60, 90 right triangle, and the short leg is a half mile. It's always half of the hypotenuse. So that's that little overlapping region. So we just do simple subtraction. Root 3 over 2r minus 1/2. So now we have our two radii. We have the purple radii, which is the mount, where the actual pendulum is being supported, and then we have the green, which is the Earth underneath the bob at the end. So the Earth is going to be moving slower, which means the bob is going to deflect to the right. All right? So we're going to figure out the circumference of the purple and the circumference of the green. Remember, circumference is 2 pi r, so there are the results there. And then we're going to find the speed. Now, the speed, we're going to do it in miles per hour, and we're just going to simplify the turn of the Earth as 24 hours. Now, technically, it's not exactly 24 hours, but just for this simple example, we'll use the number 24. It's pretty close. So we've got the speed of the Earth underneath the bob, and we have the speed of the mount, and the Earth is traveling at a slower speed. That's where the Coriolis effect comes from. So if we want the speed of the Coriolis effect, we take the faster speed minus the slower speed. Again, it is this delta speed that is the entire source of the Coriolis effect. All right, so we just do a simple subtraction. Fortunately for us, most of that stuff cancels out. All right, because our denominators are the same. And then we can cancel out even further. We got some minus signs. We got a 2 cancels with the 1/2, and we end up with pi over 24 miles per hour. So that is our Coriolis effect in miles per hour. Now that's not very helpful unless we consider the radius envelope of the swing. Again, there's that circle because our pendulum can swing in all directions, and we want to figure out what the actual precession, the period of precession is. So again, with our 14-mile tall pendulum, the radius of the swing was 1 mile. All right, so the circumference is 2 pi, or 2 pi times 1, right? So to find the time, we just do distance divided by speed. All right, so the distance is 2 pi. We're going to divide that by the speed, which is pi over 24. Now remember from from arithmetic, when you divide by a fraction, you multiply by the reciprocal. And we end up with 48 hours. 48 hours. So for our pendulum that is at 30 degrees north latitude, the period of precession is going to be 48 hours. Now that's great if you're at 30 degrees north latitude, but what about other latitudes? So now we're going to actually derive the formula. We're going to go through the same exact steps, but now we're going to use generic variables instead of actual values. All right. So now we're going to be at theta degrees north latitude. Right. So some town at theta degrees north latitude. There's our north-south swinging pendulum, and we're going to run the exact same procedure. So we'll speed things up a little bit. We'll have r sub e as the radius of the Earth. Now we need to find the radius of the turn of the mount. Well, that's going to be using trig. It'll be based on cosine of theta. We also have the swing. Now, it's no longer going to be a 1 mile swing. Maybe the swing is only going to be a couple feet, but you will end up at a higher latitude. All right, so we'll call that radius of the swing r sub s. And that gives us a similar triangle, again with theta. So the short leg becomes r sub s sine theta. That gives us our little overlap. So again, we just do subtraction. All right, so we have the two radii. And those two radii become the radius for the purple and the radius for the green. All right, so the radius of the mount is in purple, the radius of the green, which is the Earth underneath the end swing of the bob, is in green. And now we got to find the circumference. Now again, to find circumference, it's 2 pi times the radius. All right, 2 pi times the radius gives us our circumference. Now to be more specific, to be more exact, we're not going to use 24 hours for the turn of the Earth. We're going to use just a variable, or I should say a constant, t sub e, the time it takes the Earth to turn once, which is approximately 24 hours. But this is going to make our values much more exact. Again, we've got the slower speed in green, the faster speed in purple, so we're going to subtract faster minus slower to get the velocity of the Coriolis effect, which is represented by that red arrow. Remember, that green bob, the pendulum bob, is being deflected to the right. So there's the subtraction in yellow. Again, most of the stuff is going to cancel out. All right, and then we can cancel out a little bit further. Those minus signs going to cancel out. So that's what we have for the miles per hour of the Coriolis effect. Now we're not done. We need to use the radius of the swing envelope. All right, and again, that was r sub s. We didn't know how far it was swinging, so we'll just say r sub s. Now, how do you find the circumference? Well, it's 2 pi r. So it's 2 pi times r sub s. So again, distance divided by speed is time. We are interested in the time, the period. So we do distance divided by speed. When you divide by a fraction, you multiply by the reciprocal. And what we find is most of the stuff's going to cancel out. The 2 pi r sub s is going to cancel out. And we're left with t sub e over sine theta. Again, t sub e is the sidereal rotation of the Earth, or it's like 23.9 hours. 23.934 hours. It's a sidereal day. All right, so that's the time of precession. So we now have derived the formula for the precession of a Foucault pendulum. All right. Now please notice that what we did not need in this formula, we didn't need the mass, we didn't need the length, we don't even need the period of the swing or even the radius of the swing. All these terms were either never used or they canceled out. All right, so we end up with a very simple formula for our Foucault pendulum. So the last thing we want to do is find the period of precession, but we want to derive it in a completely different manner. We're going to derive it using angular velocity. So we're going to review what the right hand rule is. If you take your right hand and you curl your fingers around into a thumbs up sign, the direction of the fingers curling will wrap around the vector and the thumb will point in the direction of the vector. So for angular velocity, when the fingers are curling around in the direction of the rotation, such as the globe rotating to the east, the thumb will point in the direction of the angular rotation vector, or the angular velocity vector. All right. Now, what's the length of that vector? That's going to be 1 rotation per sidereal day. All right. And the direction is parallel to the Earth's rotational axis. So let's reorient the globe a little bit. So there's our angular velocity vector. What if we had a Foucault pendulum exactly at the North Pole? And you might have seen this, seen videos of this. Well, the globe is essentially going to turn under the pendulum. So we're going to have an equal and opposite vector for the Foucault pendulum. Now, anywhere other than the North Pole, right? Anywhere other, you have to break red vector into 2 orthogonal vectors, a blue and a green, and they have to be at right angles to each other. Now, we don't really care about the green. The blue is going to be the rotation of our Foucault pendulum. All right. So again, using the right-hand rule, taking a look at that blue vector, notice that our thumb is now pointing downwards. Our fingers are wrapping around. Now we're going to pay attention to where the fingers are going, and they're going to move in a clockwise fashion. So our Foucault pendulum in the northern hemisphere, our Foucault pendulum is going to precess in a clockwise fashion. It's going to be opposite for the southern hemisphere. All right. Please also notice that the blue vector is shorter than the red vector, which means our period of precession will be slower than the rotation of the Earth. All right. So again, let's use the diagram, very similar diagram we used with our other derivation, but this time we're using a little purple purple triangle. Now, what does the red mean? The red means the sidereal rotation of the Earth, 1 rotation per sidereal day. And the blue is representing the rotation vector of the Foucault pendulum. So if you just do the trig, it's sine theta. Sine theta times the hypotenuse. All right. So the angular velocity is going to be sine theta times 1 rotation per sidereal day. And again, the sidereal day is about 23.934 hours. How do we find the period? How do we find the period? Well, it's essentially the reciprocal of the angular velocity. So we take that and turn it upside down, and we get t sub e, or the sidereal time, divided by sine theta. Now, does this formula look familiar? It's because it's the same formula we derived when we used the Coriolis effect. So I think this is fascinating, that kind of doing a little thought experiment using the Coriolis effect we end up with the exact same formula as using angular velocity vectors. So that was the math of the Foucault pendulum. Our next video is going to explain exactly how to make your own. Now, believe it or not, there are 7 factors to consider. some more important than others. So we're going to go into great detail on that so that you can fairly easily build your own. What you do need is a very tall location. So if you have access to a barn, that would be perfect. You need an indoor location with a very, very high roof. Sometimes you'll see college students do this in a stairwell. The problem with a stairwell is usually you have like a slot, so you can't necessarily test your Foucault pendulum at different launch angles, different launch azimuths. But you'll make do with what you have. But the taller, the better. All right, so you're gonna see a lot of details in the next video, and then the third video of the series is going to be the results of my Foucault pendulum, and I may come up with a big fat failure because I literally haven't done it yet. So we'll see how that goes. So when making comments under this or any other video, please be kind to one another and build each other up. Thank you.